will talk about identification of flatbands in two-dimensional materials using neural networks. Exactly. So you have 15 minutes in total, so I suggest 12 minutes talking and 3 minutes questions. And if there are more questions, then they can be, I mean, we can discuss after the session.
All right. Thank you.
Start.
Okay, so good evening, everyone. So my talk, as you have heard, it is on identification of flat bands in 2D materials using neural networks. So first I'll talk about flat bands and motivation of our work. Then we'll talk about some attempts which have tried to find flat band materials. And then I'll talk about our approach, how we did it, and what are our results, and then outlook. So as we all know, the flat bands can show various quantum phenomena like fractional anomalous quantum Hall effect, unconventional superconductivity, anomalous Landau levels. This happens because of quenching of electronic kinetic energy of electrons, which can happen in several cases, like in case of when the electrons are densely populated in f orbitals of lanthanides, or it can also happen in case of quantum interference of electronic wave functions, which can lead to topological flat bands. It was seen in twisted bilayer graphene in 2018, but the origin of superconductivity in twisted bilayer graphene as a result of these flat bands was recently understood. So all this has fueled a lot of research into finding new flat band materials. So there can be two ways people can find new flat bands. One is to artificially engineer flat bands. A lot of work has been done there. And there are other ways by which people have tried to find flat bands in unexplored materials. One way to do that is by using numerous databases that are available right now. You can see FLO, the Materials Project, topological material database. All these databases are available, which are free to use, and it has a substantial number of band structures. So what we have done is basically we searched these databases for new flat band materials. Our work was to use Materials Project database to train a neural network algorithm to identify flat bands in these band structures. And then we used that to find new flat band 2D materials. Because we are from a flat band, we're from a 2D materials background. And then once we have the list of all the flat band materials, we then try to filter out the trivial materials which do not show very interesting physics, and try to filter out and find materials which have interesting, find out interesting materials within them. And then ultimately we go for experimental validations. So first we started with Materials Project database. As you know, the database, the band structure looks like this. So to make it easier for the machine learning algorithm, we first removed all the extraneous features, which makes the band structure look like this. And then we segregated, we divided the band structure into several small segments, which made it even easier for the machine learning algorithm to comprehend and to identify a small area which has flat band segments. So now each of these segments, work as a training example. We manually select each of the flat areas within this, like this portion which has a flat segment with it. Now, because we have already divided this band structure into very small segments, it becomes very easy for machine learning algorithm to understand, and we used a feed-forward neural network to give us output. So it had 1500 elements in the input layer, which is basically the resolution of each of the segments. And it had 100 elements in the hidden layer, just one hidden layer it had. And the output layer shows whether it is a flat band material, it has a flat band segment or not. We used a learning rate of 0.01. We varied the regularization parameter and used different training functions. And what we did, we used 20 such machine learning algorithms and took an average of it, which shows around 91.2% match, which with manual selection. We have tested that data. And interestingly, what we see is that in the training example, approximately 20% segments of have flat bands in them, which will be something which will be interesting later. I'll show you. So after this, okay, so we have got a neural network model now which can predict flat band. Now we have tried to identify 2D materials with flat bands, and we use 2D materials encyclopedia database. We took a domain of around 0.2 electron volts around the Fermi energy. And this shows a prediction like this, where the flat band segments are highlighted. And if any segment is highlighted, we can call that material to have a flat band. So we started with around 6,000 materials in the database, and we end up at around 50% of them to have flat bands in that energy range. The flat bands is not only a totally flat line; it can start to rise and get flat at some point. That will also pass as a flat band. So that's how we did it. And then we still filtered out. Then because we are working with 2D materials, we should have exfoliable materials, and we filtered out materials which have very high exfoliation energy, and we also filtered out non-radioactive materials, and we are left with around 720 materials, out of which around 150 are metallic. So once we have this approximately 700 materials, we still wanted to narrow down our research, our search, and we introduced a band flatness score. The band flatness score had two attributes. First is the energy bandwidth of a flat segment, whether a segment that is passing as a flat band, whether it's very flat or it has certain waves, or it has some waviness in that, or and the other attribute is how spread is the flat band in the Brillouin zone, whether it is spread throughout the Brillouin zone or a very small part of it. So based on that, we sorted the list of 700 materials, and near the top we get materials like this, which are very flat bands near Fermi energy spread throughout the Brillouin zone. Now this material, we can see it has a very high band gap, which is not very sometimes in many optical and electronics application. It can be it may be more beneficial to have materials with smaller band gaps or metallic materials. So we further filtered out materials which have less than 1 eV band gap, and we're left with 256 materials. So these 256 materials is now a good starting point to work. Now a good starting point to work manually on each of them and to look for interesting materials. So what we now are doing is basically we started to synthesize some of the materials in our laboratory, and we are expecting for experimental validation of it. So that's it. Thank you.
Okay, thank you for the nice talk. So are there questions? We still have plenty of 4 minutes.
Yes.
So I don't see any hands raised. Now Sergey Flach has a question.
Yeah, thanks. Very interesting talk. Can you explain again? So go back to this slide where you explained how you were training the network before. Yeah, probably here. So again, on input you give, if I understand correctly, you give images of these segments of the band structure. Is that correct?
Yes, exactly.
And then you label the entire. But okay, these many segments all belong, let's say, to one band structure.
Yes.
So one group, and the entire group is called has a label which is now either yes or no, or 0 or 1, or flat band or no flat band. Correct?
I have done
so let's say, what is getting the label? The entire group of these pieces?
No, only one segment. Each of the segment has a label. Initially, so I only had to mark which had a flat band. So otherwise, if we don't mark it, it obviously deemed as a non-flat band. So each of the segment has a label. Now, yes.
Go ahead.
Yeah, and when I see when I did it, apply it on some, so it took the band structure from in this energy range, and it divided into several segments, these 5 segments, and tested on each of them whether they're flat or not. If this segment, among these 5 segments, if anyone has a flat segment, the material is deemed to be a flat band material.
Okay, and fine. And then I'm not sure yet how you are now going to use this to predict. So this is the training. So now what are you doing?
This is the training. This one is the training.
So what do you put in on when you do the test, so to say? So
what I did was I tried to train the material based on Materials Project data. So I have downloaded approximately 5,000 materials, band structures like this. Not 5,000, around 3,000 material band structure like this, and I have then used those to train my data. And then application was done on 2D Materials Project, 2D Materials Encyclopedia.
Yeah, sure. But what you now want to do once this machine is trained is to run it on some samples. And what is a sample? It's again a piece of a band structure. Is that correct?
Exactly. Yes.
I see. I mean, somehow, what's then the purpose of that? To be faster than the eye? Because I can, of course, also look with my eye and say, oh, here's a flat band. So
yeah, so the purpose of this is that if you see in this Materials Project or FLOW, they have very huge number of band structures. It cannot be done manually. So it has to be some machine learning algorithm that can
I see. It could be very interesting maybe to design a trained program which is capable of making a correlation to the, I don't know, the crystal structure.
Yeah, yes, it has been done actually. It has been done in this work, which has just published maybe 2-3 days back actually, this work. So they have tried to link that to crystal structure, and they have tried to find Kagome lattice and other sources of topological flat bands in those crystal structures, and then linked it with the flat bands. So that had a different approach from crystal structure point of view, but we have taken a different approach.
I see. Thank you very much.
Okay, there's another question from Alexei. So please unmute and ask.
Yeah, thanks. Thank you for a nice presentation. It's actually a follow-up to Sergei's question, the very last one. So with this 256 candidates, did you try and see if you can somehow classify and guess what are the features responsible for the emergence of flat bands?
Yeah, so basically now I have tried to do something which is not yet complete. So what I'm trying to do is basically use clustering kind of algorithms, which can find, maybe based on stoichiometry or maybe based on crystal structure, if I can find clusters of material which have flat bands. So that I'm trying to do, not just to 256, because I'm trying to use it on these 700 materials because they all have flat bands, or maybe 3,000 materials actually. So I'm trying to use a clustering mechanism to
so you're basically, so you're trying to relate it to some properties of the crystalline structure.
Exactly.
That's right. Okay, yeah, thanks. Would be very interested to know the outcome.
Yeah. Okay, so no more questions. I don't see any. I mean, Alexei still has his hand raised, but otherwise.
No, that's because I mean, I'll lower it.
Okay. So then let's thank Anupam again.
Thank you.
And so then we can continue with the next talk.